We're going to be discussing endocrinology. Endocrinology is the system of hormones. Now, before we get into all the different hormones of each different system, we have to first understand the basics and the fundamentals of how hormones actually work. Now, many students think that hormones actually go and directly control the cells, protein synthesis and etc. What we're going to discuss. That's actually not true. Hormones really just are messengers. You see, what hormones do is, of course, hormone is number one. The first thing you have to understand is that hormones have a very specific receptor made for itself, okay? Now, once hormone basically stimulates its receptor, there's going to be a domino effect of different proteins, different enzymes that are going to eventually lead to the synthesis and all the different changes, of course, to the hormone and what its job to do for a cell is, okay? Now, before we get started and talk about all the different receptors and how ligands act, we first understand the fundamentals of endocrinology, okay? And there are really three rules. The first rule you have to understand is that within a cell, within our body, there are a lot more receptors present than hormones. In other words, receptors are usually not 100% saturated. And that's very important to understand because if, let's say, I have to increase, I really want to have a very high outcome of, let's say, I need, beta receptors of my heart leading to increased heart rate. So instead of, making new receptors, what I could do is I could just release hormones. So if we have all the pre-made receptors on the cell, it's much easier and it's much more convenient for us just to release hormones to stimulate those receptors, okay? That's rule number one. There are much more receptors than hormones. The second rule is the rule of what it has to do with is that the downregulation and the desensitization. See, normally receptors, if you constantly stimulate receptors, what's going to happen is that the receptors eventually are going to become so sensitive anymore, and eventually our cell, our genetics, are going to stop synthesizing those receptors, okay? That is known as downregulation and desensitization, okay? And vice versa, the same thing happens with the exact opposite. Let's say, for example, I didn't use a receptor for a long time. For example, we're going to discuss in cardiology. Let's say a person's on a beta blocker. So if we block this receptor is being used anymore. Therefore, what's going to happen is let's say I immediately remove the beta blockers from the patient. So these receptors are going to be extremely sensitive, and therefore, when a ligand will stimulate it, we're going to have a massive effect. Okay. And the third rule in endocrinology is what is known as a permissive effect. A permissive effect that we're going to discuss later on in the lecture, specifically cortisol and T3 and T4 are able to basically sensitize the receptors. For example, normally if a ligand will bind to a receptor, so eventually we're going to, let's say, have 100% of outcome. Now, if let's say I have a permissive effect on the receptor, what's going to happen is instead of having, let's say, 100%, I'm going to make the receptor so sensitive that I'm going to have, let's say, a 300% effect, and of course I'm going to increase whatever I'm supposed to do. Okay? Those are the three rules you have to understand. Now, regarding the different hormones, of course, hormones can be split up into water-soluble and lipid-soluble. Okay, now why is this important? Is because the lipid-soluble, first of all, what are the lipid-soluble hormones? Well, lipid-soluble hormones are all hormones derived from cholesterol. Testosterone, estrogen, progesterone, let's say aldosterone, cortisol, vitamin D, retinoic acid, and T3 and T4. Okay, every other hormone, every other ligand in our body is going to be water soluble. Now, this is important to understand is because remember, we said in order for hormones to work, they needed actual receptors. Now, the receptors for which water-soluble hormones, because water-soluble hormones cannot get through the bilayer membrane, they have to stimulate the receptors on the outer membrane. Of course, while, let's say, a lipid-soluble hormone can go and actually stimulate receptors, well, depending on which hormone we're going to deal with, either can do intracytoplasmic or intranuclear. Okay, so first we're going to talk about the water-soluble hormones and the extracellular receptors. So now, there are two really main classes of extracellular receptors. We have our serpentine receptors. There are 3 serpentine receptors, and we have 4, which are known as one-pass receptors. Okay, the 3 serpentine receptors are referred to as number one. It's called serpentine receptors because also referred to as a 7-transmembrane receptor. Because what happens is that the receptor goes through the membrane 7 times. Okay, so these are known as serpentine receptor, also the 7-transmembrane receptors. Now, there are 3 different serpentine receptors, okay, based on the different G proteins that they're coupled with, okay? So all of these are going to be G proteins. Now, depending on which G protein they're coupled with, that's going to be the name of the receptor. So the first receptor is known as the GS coupled, therefore it's going to be a serpentine receptor, GS. Okay, the second one is going to be a GI coupled, therefore it's going to be a serpentine receptor, GI, and the third one is going to be a GQ coupled, so therefore it's going to be a serpentine receptor that is GQ. Okay? Now, first let's talk about the GS receptor. Now, I have to say that most hormones in our body actually stimulate the GS receptor, okay? And what happens is when the specific hormone goes and binds to the ligand binding domain, which is, by the way, the domain it binds to, of course, this is going to lead to excitement and excitement of this tail of this receptor, which is actually occurring intracellular. And what's going to happen is that, remember, it's attached to a very important protein known as the G-stimuli protein. Before we discuss all about what happens, first we need to discuss about this G protein. This G protein is made up of 3 different segments. It has an alpha unit, a beta unit, and a gamma unit. Okay. Normally, all the alpha, beta, and gamma are connected. Okay. The reason why they're connected is because in the alpha unit there is going to be a GDP within it. Okay. This is actually a low charge molecule. Therefore, they're able to stick together. However, when we stimulate the serpentine receptors, that's GS, what's going to happen is that this portion is going to tickle the alpha portion. And when it tickles the alpha portion, what's going to happen is GP is going to leave the site of the alpha portion. And what's going to come in is going to be GTP. And because GP is now very strong, it's not strong, but it's very charged, what's going to happen is that the alpha doesn't need the beta and gamma anymore. Therefore, it's going to leave. Okay, and when it leaves, it's going to stimulate a very important enzyme referred to as the adenylyl cyclase enzyme. Okay, now this enzyme, once stimulated, is responsible for taking ATP. It's going to take ATP and it's going to break it down into what is known as cyclic AMP or CAMP. Okay. Now, before we discuss what CAMP does, you should understand also that in order to regulate the system, once we have our active alpha subunit, what's going to happen is that this portion is going to go and it's going to actually break down the GTP back into GDP. Why are we doing this? Because again, we don't want constant stimulation of the adenylyl cyclase because we don't want to have increased levels of cyclic AMP. Now, once normally, for example, let's say we have the GS stimulating the alpha subunit, we stimulate the adenylyl cyclase, which breaks down ATP to cyclic AMP, then the cyclic AMP levels are going to be high, and this is going to go to a very important protein known as the protein kinase A protein. And protein kinase A is going to do 3 major things. The first thing it's going to do is going to go to the different channels within the cell. It could be a sodium channel, calcium channel, magnesium channel, chloride channel, whatever that hormone is really linked up to in a specific cell, that's really what channels it could really start affecting. Okay, that's the first thing it's going to do. Second thing it could do, it could actually go to different enzymes in the body. And in the different enzymes, it could go and it's going to phosphorylate the different enzymes. Now, depending on the different enzymes, some enzymes when you phosphorylate them, they get active. Some enzymes when you phosphorylate, they actually turn off. So again, depending on what the cell needs, depending on what this receptor is really for, that's where we're going to be changing within let's say the enzyme's function. Okay, and the third thing we're going to do is we're going to go to the genetics of the cell. And in the genetics, of course, we're going to translate. We're going to make NMRA, and eventually, what we're going to do is we're going to make the different proteins. And of course, these proteins are going to aid in whatever the cell needs. Okay, that is protein kinase 2, and that is the GS of the first serpentine receptor. Now, the second serpentine receptor is known as GI, also known as G inhibitory. And of course, let's say, for example, something goes and stimulates the GI. What's going to happen is, of course, is that this receptor is going to activate. What's going to happen is at the end of the tail of the receptor is going to stimulate the alpha portion of the G protein. And of course, in that is GTP. GTP is going to leave, and inside is going to become GTP. When GTP comes, what's going to happen is that the alpha subunit is going to leave from the this G protein complex, and this time it's going to go and it's going to inhibit the adenylyl cyclase. Well, before, remember, it's stimulated, and when it inhibits the adenylyl cyclase, we don't break down ATP to cyclic AMP. Therefore, we don't stimulate protein kinase A there. Therefore, we're going to decrease all these processes. We're going to really, it's more like the inhibitory of the G stimulatory. Okay, this is how we regulate it. In addition, also the beta subunit and the gamma subunit. Remember, this is G negative. Are going to both go, and they can actually work on specific potassium channels. And of course, if you open up a potassium channel, what happens is because potassium is more within the cell, therefore we're going to have efflux of potassium, and of course the cell is going to be hyperpolarized. Okay, and when the cell becomes hyperpolarized, all the functions are going to be decreased. Okay, that is the second serpentine receptor. The third serpentine receptor is referred to as the GQ. The GQ, this is the GQ protein. Again, it's the same thing. It's made up of 3 portions, the alpha, beta, and the gamma. Of course, when the specific ligand goes and binds to its domain, this portion is going to get active. When it gets active, again, GTP is going to go out, and GTP is going to come in. Okay, when GTP comes in, GQ is going to go away, and GQ, this time, activate a very, very important enzyme known as phospholipase C. Now, phospholipase C loves to eat lipids, okay? And there's no better place to eat lipids than the cell membrane, okay? And it's going to go to the cell membrane and it's going to break down a very unique, specific lipid referred to as PIP2. PIP2 stands for phosphatidyl inositol paraphosphate, okay? And it's going to break it down into two different things. The first one is IP3 and DAG. IP3 stands for inositol paratriphosphate, and DAG stands for diisoglycerol, okay? Now, these two proteins, these lipids really, are extremely important. IP3, the first thing it's going to do, it has receptors on the endoplasmic reticulum, okay? The endoplasmic reticulum, like we'll obviously discuss in other lectures, is responsible for all the calcium within the cell. And of course, when it stimulates it, it's in this receptor, this endoplasmic reticulum is going to pump out calcium out into the cell. Okay, now once calcium is into the cell, it's going to move to a very important protein known as the chemomodulin protein, okay? And it's going to basically stimulate this protein. And when this chemomodulin protein is going to stimulate, this is going to stimulate a very important protein referred to as the CAM kinase enzyme, okay? And this CAM kinase is then going to go, just like the protein kinase A, it's going to phosphorylate the different channels, it's going to stimulate the different enzymes, and again, it's going to act on the genetics to alter and really regulate what that cell specifically needs, okay? Now, regarding DAG, acetylglycerate, this actually will go together with the calcium. Calcium will actually go together with DAG, and this is going to go to a very important protein, which is referred as protein kinase C. Okay, and protein kinase C, again, also like protein kinase A, will also go and we'll start working on the channels, we'll start working on the different enzymes, and of course we'll start working on the different genetics within the cell. Okay, and that is basically the serpentine receptors. Okay, now the next group of receptors are going to be the one-pass receptors. Now there are four one-pass receptors. We have number one, we have the tyrosine kinase receptors. You have the tyrosine kinase phosphorylated enzyme receptors. The third type, you have the tyrosine kinase associated receptors, and the fourth type is you have your guanylate cyclase receptors. Okay. The first one again is going to be the tyrosine kinase. Tyrosine kinase receptors is mainly for insulin and all growth factors. Okay, all growth factors. Growth factors meaning, let's say, platelet-derived growth factor, fibroblast growth factor, all those type of growth factors will go and can stimulate the tyrosine kinase receptor. And of course, when it stimulates it, now normally the receptor, because with only one pass, it really has two legs over here. And when this enzyme gets stimulated, the legs are going to start becoming together. And when the legs become together, they're going to stimulate a very important protein, which is referred to as the tyrosine kinase portion. Okay, and this tyrosine kinase portion, you should understand that throughout this portion, you're going to have these tyrosine molecules over here. And obviously, when the ligand will go and it will stimulate it, this is actually one of the most unique enzymes in our body because this goes through a process known as autophosphorylation. Autophosphorylation is really when an enzyme can actually stimulate itself. And what's going to happen is that this tyrosine kinase is going to phosphorylate these tyrosine molecules on them. Okay, and this is actually very unique because usually this doesn't happen within our cells. Okay, now once the tyrosine kinase is going to be phosphorylated, a very important enzyme, a very important protein known as sulfhydro-2 (SH2) has these receptors for and these sensors for anytime tyrosine is going to be phosphorylated. And SH2 is then going to go and is going to bind to the tyrosine activated phosphorylated portions on the tyrosine kinase. Okay, and once this happens, it's going to do two major things. The first thing it's going to do is going to stimulate a very important protein known as son of 7. Okay, it has a very weird name referred to as son of 7. Okay, when son of 7 is active and it gets stimulated, this is going to stimulate its father. This is going to stimulate what is referred to as the RAS protein. Okay, now this RAS protein also has a pocket. Okay, and this pocket also has GTP in it. Now, when this cell gets stimulated again, GTP is going to go out of the cell, GTP is going to move in the cell, and when this cell has GTP, it becomes active. When it becomes active, it's going to stimulate his father, which is referred to as the RAF kinase protein. And this RAF kinase protein, again, once it gets stimulated, this is going to go and stimulate its father, which is known as the MAP kinase. Okay, and this MAP kinase is the important one. This is the one that's going to go to the cell, activate the genetics, it's going to stimulate the different proteins, and of course it's going to go in and work on the different transporters within the cell. Okay, now so that is the first thing of SH2 to do. The second thing that SH2 likes to do, and especially it's very important with insulin, this likes to go and also stimulate different protein phosphatases. Okay, and of course, like we can discuss later on with insulin glucagon. Glucagon has phosphorylation, and insulin has to antagonize that by stimulating this protein phosphatase enzyme over here. Okay, so that is the first tyrosine kinase receptor. Now the next tyrosine kinase receptor is the tyrosine kinase phosphorylation receptor, and basically what this does, anytime you have a, let's say, a ligand binding to this, what's going to happen again, it's called the tyrosine kinase because it's very similar to it, but again, once it's activated, basically this is going to go and has a lot of phosphorylation properties, and it could go and phosphorylate, different proteins, different enzymes within the cell. Again, you should know that this cell is very important within white blood cells, specifically macrophages. We'll discuss this when we deal with the immunology. Okay, now the third type of single receptor is referred to as to be the tyrosine kinase associated receptor. Now these receptors is made up of two different portions. It has a body, which is the ligand binding domain, and then it has two legs. Now, attached to each one of these legs is a very important protein referred to as the JAK kinases. Okay, JAK kinase stands for the Janus kinase, and normally what these things do is they leach onto each leg. Now, normally when a ligand will go and bind to its domain, what's going to happen is that these legs are going to be sensitive and they're going to be stimulating these JAK kinases. And when these JAK kinases are stimulated, they're going to do actually something very strange. They have a tail which is going to phosphorylate the contralateral leg. Okay, so the right is going to do the left, left is going to do the right. And once these legs are phosphorylated, what's going to happen is there's a very important protein known as the STAT proteins. Okay, these STAT proteins, which stands for single transducer activations of transcription, is basically has senses for these phosphorylated legs. And what's going to happen is that they're going to bind to these legs, and when they bind to these legs, it's going to be activated. And when they activate, they're going to start fusing together. And when they fuse, only once they're together, they're going to go down all the way to the nucleus. And of course, they're going to act on different enzymes. They're going to lead to phosphorylation. They're going to make different proteins, and of course, they'll phosphorylate different channels. Okay, and the last of the one-pass receptors is referred to as the guanine cyclase receptor. And of course, this receptor actually is really for only ANP, atrial natriuretic peptide. Okay, and what happens over here is that, of course, once the ligand binds to its receptor, of course, this is guanine cyclase, so it's going to break down GTP to cyclic GMP. Okay, and high-level cyclic GMP is going to stimulate the protein kinase G, and of course, protein kinase G will then, of course, move down into the cell, of course, activate genetics, it will activate enzymes, and of course, it's going to lead to phosphorylations of different channels. Okay, so that are the one-pass receptors. Okay, now, so the water-soluble hormones, of course, bind to the has to bind to extracellular receptors because they cannot get into a cell. However, if let's say the lipid-soluble hormones, because they could diffuse through the membrane, they're able to go and bind to a receptor inside the cell. Now, all the lipid-soluble hormones basically bind to a intracytoplasmic receptor, which is located, of course, in the cytoplasmic. Only the T3 and T4 can bind to the intranuclear receptors. Again, they're basically the same and they really function the same way. Okay, now these receptors are made up of three different portions. Of course, you have your ligand binding domain. Okay, or we'll do it over here. We have your ligand binding domain over here. Okay, then you have a very portion which is the DNA sequence we refer to as the zinc fingers. Okay, these zinc fingers are basically the DNA sequence readers, which is able to translate a very specific sequence of DNA. Okay. Now, what's very important is on top of this zinc fingers, there's a very important protein called HSP, heat shocking protein. Now, normally this HSP acts as a barrier around the zinc finger, so we don't just start transcripting and translating the different genetics. However, once the ligand goes and binds to the ligand binding domain, once, let's say, the T3 and T4 bind to its ligand binding domain, what's going to happen is that this HSP is going to move off of the zinc fingers. And of course, once the zinc finger is free, it's going to go and bind to the specific DNA sequence, and of course, we're going to translate different types of proteins within the cell. Okay? Now, that is how the lipid-soluble or hormones work. Now, there's also another way for hormones and different ligands to actually interact with the cell, is that through the different channels. Okay? Now, the same way, well, in some situations, for example, let's talk about GABA. GABA, for example, of course, will go and bind to its receptor. What type of receptor? The type A receptor actually has a ligand binding domain which is on a channel. Instead of it being into a cell leading to, let's say, this whole process, what's going to happen is it just stimulates the channel, and the channel is now going to either open or close. Now, when GABA stimulates this receptor, which is on the chloride channels, chloride is going to start going into the cell. And of course, when chloride comes into the cell, this obviously is going to lead to the hyperpolarization of the cell, therefore inhibiting a postsynaptic neuron. Okay, and vice versa also with, let's say, glycine. Glycine also basically has a ligand binding domain on a chloride channel. And regarding the stimulation, for example, let's say glutamate. Okay, glutamate obviously will stimulate the NDA receptors, which basically are receptors that are on ion channels. And of course, when it stimulates its ligand binding domain, of course, this is going to lead to the influx of calcium. And when calcium gets into a cell, of course, this is going to lead to increased resting memory potential and obviously leading to depolarization. The same thing with serotonin. Serotonin also, of course, can bind to its receptors over here. And when it binds to its receptors on the ion channels, this, of course, is going to open ion channels, and this is going to lead to influx of sodium within the cell. And, of course, this will eventually lead to the depolarization of the cell. Okay? So just note that hormones could actually bind to extracellular receptors, which can lead to all these processes, or it could even bind to the ligand, which is on the ion channels, which of course could affect and alter the different channels to change the electrophysiology and electrical potential of the cell membrane. Okay. Now the last system we're going to talk about is nitric oxide. Now nitric oxide, of course, is lipid soluble, so it's able to diffuse through a cell. Now once it diffuses through the cell, it's going to stimulate a very important enzyme, which is, like we saw, the guanine cyclase enzyme. Okay. And of course, when this enzyme gets stimulated, it's going to break down GTP into cyclic GMP. And cyclic GMP again is going to stimulate the protein kinase G. Okay, now protein kinase G, well, specifically in the different muscles, like smooth muscle of the arterial lymph and the veins, what's going to happen is that this enzyme is now going to inhibit a very important enzyme known as the myosin light chain kinase. Okay, now normally this enzyme or this protein is responsible for going and leading to the contraction of the smooth muscle. Okay, leading to, let's say, arterial contraction or venal contraction. So if protein kinase G inhibits this enzyme, we're not going to have contraction. And when we're not going to have contraction, we're going to have vasodilation. Okay, and that is how we dilate the vessels. Now, what's extremely important, and this they actually like to ask a lot, in order to regulate this system, and what breaks down cyclic GMP, again, because we don't want cyclic GMP to stand all around forever, so there's a very important enzyme known as the phosphodiesterases, okay? And what these enzymes do, specifically the one that you really should know, are the type 5 ones. Okay, the type 5 ones are actually found in the penis, and of course they actually go and lead to the erection, or actually really they prevent the erection, okay? Now, there's a drug called Viagra, like everyone sure knows. Viagra basically inhibits this enzyme, and when this enzyme is inhibited, we're going to have high levels of cyclic GMP, which means we're going to have high protein kinase G, which means we're going to inhibit the myosin light chain kinase for a longer while, so we have a sustained erection. Okay, so that is basically how hormones really influence the cell. Now, before we get on to the actual clinical during the next lecture, I just want to quickly go through the different receptors, which and really group them as which specifically G protein they're coupled with. Okay, so regarding the GABA receptors, again, we said GABA A receptors are actually on chloride channels. The GABA B receptors actually are serpentine receptors, which are GI coupled. Okay, so the GABA B are GI coupled. Regarding the alpha 1, again, remember the autonomic nervous system is made up of two different portions: sympathetic and the parasympathetic. The sympathetic is made up of the alpha and beta receptors, and the parasympathetic is made up of the muscarinic receptors. Now, regarding the alpha receptors, you have two types: the alpha and the alpha 1 and the alpha 2. Alpha 1 receptors are going to be GQ coupled, alpha 2 receptors are going to be GI coupled. Okay, regarding the beta receptors, you have a beta 1 and beta 2. Beta 1 is going to be GS, beta 2 is also going to be GS. In addition, you also have a beta 3 receptor, which is really a modified B2, and that really is also going to be GS coupled as well. Now, regarding the muscarinic receptors, we have three types. We have M1, M2, and M3. M1 is going to be GQ coupled. M2 is going to be GI coupled, and M3 is going to be again GQ coupled. Okay. And lastly, regarding the dopamine receptors, there's two types. You have dopamine 1 and dopamine 2. Dopamine 1 are going to be GS coupled, while dopamine 2 is going to be GI coupled. Excuse me, GS coupled is D1, and D2 is going to be GI coupled. Okay. And that is how the receptors and the different hormones.